This subtopic covers constructive and destructive interference. By the end of this subtopic, you will be able to define coherence and state the conditions for both constructive and destructive interference. Interference is the phenomenon where two or more waves overlap in the same region of space. It is divided into constructive and destructive types. For stable interference patterns, overlapping waves must be of a similar type, be coherent, and have comparable amplitudes. Constructive interference occurs when two waves of the same amplitude and frequency arrive in phase. The resultant wave's amplitude is the sum of the individual waves, reinforcing each other. Destructive interference happens when waves arrive at a point in antiphase, 180 degrees out of phase. The crest of one wave coincides with the trough of the other. This results in complete cancellation.
This part is about the interference of light. We will specifically explore interference in double slits, thin films, air wedges, and Newton's rings. When light strikes a double slit system, it diffracts and forms two coherent circular waves. These waves overlap, creating an interference pattern of bright and dark fringes on a screen. The position of bright fringes is given by y sub m equals m lambda d over d, and the position of dark fringes is given by y sub m equals m plus 1/2 lambda d over d. Let's review an example problem. In a Young's two-slit experiment, we have the separation between the two slits at 0.20 millimeters and the distance of the screen from the two slits at 55 centimeters. The distance between the mth bright fringe and the n plus 10th bright fringe is 11.4 millimeters. We will calculate the wavelength of the monochromatic light using the bright fringe formula. This part will cover the interference of reflected light in thin films. When light is incident on a thin film, bright and dark fringes will be formed. Reflection at the first surface involves a phase change of pi radians. At the second surface, there is no phase change. We see the conditions for constructive and destructive interference. Here is an example problem. We need to calculate the minimum thickness of a titanium dioxide film with a refractive index of 2.4, coated on a glass prism to completely reflect red light of 680 nanometers. The prism's refractive index is 1.50. We use the destructive interference formula and set m equals 0 for minimum thickness, which results in a thickness of 71 nanometers. This part examines the interference of reflected light in air wedges and Newton's rings. Newton's rings form when light is incident normally on a glass lens placed on a flat glass surface. The principle is similar to the air wedge, but the pattern consists of concentric rings instead of parallel lines. The key equations for bright and dark fringes are also presented for both phenomena. Here is example 20. We will calculate the diameter of a wire used to form an air wedge. Given the length, wavelength, and number of dark fringes, we apply the dark fringe condition for an air wedge, 2d equals m lambda, to solve for the diameter.
Thank you for your time, and bye.